Okay, this is 5.5, solving rational inequalities. So we looked at kind of the same idea in the last section, but we had an equal sign here. Now we're going to deal with inequalities. So it's a statement that one rational expression is less than or greater than another rational expression. Yeah. Yeah. Okay, the goal is to solve rational inequalities using algebraic and graphical approaches. So if anybody asks you what the goal today is, you'll say to solve rational inequalities using algebraic and graphical approaches. All right. So we have two functions here, P and Q. Okay, both rational functions. So quotients here. And then the question reads, determine when the time period when the population of New Ironfield, which is this one, is exceeded the population of Nickelfield, which is this one. So we create an inequality that looks like this. Okay, this value is greater than that. I think that's pretty simple so far. Now in the last section, what would have you done next? What would have you done next? Somebody tell me. In the last section, what would have we done? Yeah. Yeah.
Me?
Yeah.
Oh, I would have multiplied the product of the denominator.
Good. The product of the denominator, you'd multiply both sides, or you might want to draw, you know, both expressions to one side of the inequality or equality first, right? So we've done that here. Okay. So we draw the inequality. Oh no, actually, sorry, they left them on the same side, and they did exactly that. They multiplied by the product of the denominator. Okay. That allows us to cancel out values and no longer have any fractions. Once we've done that, we can gather all the terms to one side, expand, simplify, and we end up with this, which I think is extremely straightforward. Next step is you want to always look for a common factor, which in this case is the 20. So we're left with t squared minus 4t minus 12, which is easily factored to t minus 6 and t plus 2. Okay, so everything up until there has been kind of a repeat from yesterday. Now the difference is we want to find when this value is less than 0. So we set up that table that we've learned. We learned kind of a similar way to do this when we were looking for positive and negative values of y. Now we're looking for when is this value less than 0. So it's actually the exact same way. So we put the factors on the left. So here's the factors. Okay, this 20 wouldn't have mattered, right? Because a negative number times a positive number is still going to be negative. A positive number times a positive number is still going to be positive. So you could have left that 20 out. That doesn't matter. Next is your factor t plus 2, which is here. And finally, t minus 6 is here. And then the product of them, which is here. Okay? So we're just going to sub in now values that are within these ranges and determine whether they're positive or negative, and then look at the final product. Okay? So the only tricky part then may be to find these factors, negative 2 and 6. Okay? But they just come from this equation, setting it equal to 0, solving t plus 2 is equal to 0, so t is equal to negative 2, and t is equal to 6. Okay? They come from that equation, right? Right up there. Okay, once you have those factors, those are the ones, because those are the zeros on the graph. Those are the ones where you want to check the ranges before, between, and after. Any questions about that? What we've done, or why we're doing it? The whole point is to find out the product, whether it's going to be positive or negative. And in this case, once we have this part, you need to go back to the original question and say, okay, what am I looking for now? Well, I'm looking to find when is this whole equation less than 0. So when is it negative? It's negative here. Okay, this is the only time it's negative. So that would be my range. Okay, from negative t is greater than negative 2 and less than 6. So in a word problem, you would have to go back then to the original question and say the population of New Ironfield exceeded the population of Nickelfield for 6 years after 1997 until 2003. And these years come from, again, the original question where it says t years after 1997. Okay, any questions about that? We don't consider negative values of t because, again, by definition in the equation, t is value years after 1997. So you can't say because t is negative, you're going back to 1995. No, that equation is not valid for years prior to 1997. Could have been a whole different function then. Okay? That's why it's only 6 years. Okay, for 6 years and not 8, even though this range is 8. You guys understand that? Okay, sure, I'll repeat that. We don't consider -2 and -1t and say that those are the years prior to 1997. You might want to, you might be tempted to do that because if t is the years after 1997, if I have a negative value of t, you might say, well, that was 1996. No. The reason why is because this equation models population after 1997. Before 1997, it could be a different equation. It could be a different model. Okay? So any value before 1997 is not valid. All right? Just generally speaking, you have a negative time value, it's not valid. Okay? Even though this is in reference to a year, you can't just go back years. Any questions about that? All right. So solution B, solving a rational inequality by graphing two rational functions. So what they do here is they graph Q and P separately, and then they're going to look at the range, or sorry, the domain at which Q is greater than P, and that will be their answer. Okay? So again, with a graphing calculator, it's pretty simple, right? It's very short. From the graphs, Q is greater than P for 0, where t is greater than 0 but less than 6. Okay, so we get the same answer. And that's again just from plugging into a graphing calculator, calculating Q, calculating P. This is Q, and this is P, and seeing this is the domain at which Q is greater than P. Okay, and they cross at 6. All right. Finally, C, they solve a rational inequality by determining the zeros of a combined function. So now, rather than graphing both functions, they combine the functions and set them equal to 0, and then look where that value is less than 0, or in this case, greater than 0, the way they've combined it. Okay? So they combine the two functions into a single function, will have positive values. So when Q is greater than P, f of t will have positive values. Okay? And then so they're just looking again, that same range there in the combined function. Okay? Any questions there? All right. Selecting a strategy to solve an inequality that involves a linear function and a reciprocal function. All right, so algebraic is really, the only strategy I'm going to be testing you guys on. So this is the one we want to focus on, right? In both scenarios, solution A. So it's important before you start the equation to recognize that this equation will have no meaning at the value of x equals 0. Okay? You have to identify that right away. There's a vertical asymptote or some sort of discontinuity at x equals 0 because we're going to have the value be undefined. You can't divide anything by 0. So you want to say that right away. X cannot equal 0. Okay? This comes into play later when we check our ranges on that table. We have to consider that point as well. All right, so there we say x is not equal to 0. We bring everything to one side. Now, yesterday, it would be very tempting to multiply this by x. Right? That would be kind of the idea, right? And then we get x squared minus 2x minus 8 is less than 0. Anybody tell me why we can't do that with an inequality? Why could we do it with an equality when this is equal to 0? That would be fine, fair game. But now it's inequality, we can't do it. Nobody? What's the one thing we know about inequalities? There's like only one part to it. Gianluca, yeah?
One side is greater or less than the
Okay, yeah, that's true. But no, there's one kind of trick that we have to remember with inequalities. Yeah, Marco.
Multiply it by a positive, then you also switch the sign. If you multiply it by negative, you have to switch the equality symbol.
Right, so why then can you not multiply this all by x? Right, what if x is negative in this case? Then this sign would switch. That's going to mess us up, okay? The reason why we were able to do it in the last question was why? No.
You had
No. Why? Right, because time could only be positive. Good. This case, we don't know if x is positive or negative, so we can't go ahead and multiply everything because it's going to mess up our inequality. Does that make sense? So, believe it or not, that seems like a, you know, a simple idea and yeah, no problem. It actually changes fundamentally how we need to attack this problem now. Because we have to find a common denominator and we have to go a whole different route than just canceling. Okay, than just crossing out values. So it's a much bigger pain in the ass dealing with this inequality because of that reason. Okay, so that's why rather than multiplying by x, we draw the 8 minus x to the other side, but now we need to find a common denominator. So we need to put everything over x. So we're almost doing the opposite. Rather than getting rid of it, we're having to add it to every term. Why do we do that? Is so that we can combine the numerators. Okay? And everybody remembers this from, you know, really basic fractions. You have to find a common denominator. How do I do that? I multiply each one of these numerators by x so I can put them over x. So everything here is getting multiplied by x over x, which is essentially 1, right? When I multiply stuff by 1, I can be selective. I can just multiply this by x over this and this by x over x. I don't have to multiply this by x over x. It's not going to do anything for me. Okay? So I multiply these two terms by x over x. I get x squared over x minus 2x over x minus 8x. And now these denominators are all the same, so I can combine them and join the numerators. Now my numerators are joined, I factor them, and I'm left with this equation. Any questions to there? Okay. Once I have that equation set up, I'm going to put it over here. Once I have that equation set up, we have to again go, unfortunately, to our table. Okay? Now the values you need to consider are the x-intercepts, which are going to be 4, negative 2, and the original 0. The original 0 from up here. Okay? So those are our ranges, negative 2, 0, and 4. Any question about that? Because if you don't identify those correctly, everything else is going to be wrong. So again, where do these numbers come from? They come from the zeros, so setting this equal to 0, setting this equal to 0, and then knowing that x at 0 is undefined, so it has to be a boundary in our chosen ranges. Okay? We set up the products or the factors on the left-hand side, and we figure out the product here. Whenever it's, in this case, again, negative is the ranges that we're looking for. Okay, and that's because it's less than 0. If this was greater than 0 over here, we would be looking for the positive values here. Here and here. Any questions about how you create this table? Okay, you know how to sub in values here, right? All done in your head. You're subbing in negative 3 here. Negative 3 minus 4 is a negative. You're subbing in negative 1 here. Negative 1 minus 4 is negative. Okay? No questions about that? It's simple, right? I don't have to review that. That's from kind of last lesson. All right, good. Same idea now using graphing technology. Okay? We have two functions, f at x and g at x. We graph them, and then we look for the areas on the graph where f is less than g. Okay? And that'll be the range. Okay? So it's between negative 2 and 0. So there's our range. Okay? That's the only area where this graph is less than this graph. Okay? And the same idea in the third solution, I believe, oh, they didn't do it, but they could have brought them both over and made one graph and then looked at the x-intercept like they did in the last problem. All right, determine the solution set for an inequality that involves two rational functions. So now Now we have two rational functions on either side of inequality. So in the last section, in 5.4, we would have just multiplied all this by the product of the denominator. Again, we can't do that now because it's going to mess with our inequality. So instead of doing that, what we actually need to do is we need to find a common denominator. So common denominator between these two is going to be x plus 1, x minus 3. Okay, so that's what we're doing over here. First, we move everything to one side. And now to subtract these two terms, we need to find this common denominator. So this numerator has to be multiplied by x minus 3, and this numerator has to be multiplied by x plus 1 to get a common denominator of x minus 3, x plus 1. Marco?
So, sir, you can't multiply anything by x alone, but you multiply by polynomial?
By a polynomial? No, we can't. We're not multiplying by the polynomial. No, we can't. We're not here. We're finding a common denominator. So I'm not changing. When I find a common denominator, remember, I don't change the expression at all. It's like changing 1/2 to 2 over 4. I'm just changing the denominator. Okay? I know what you're saying. So Marco's saying, well, you are multiplying it by x minus 3. No, I'm not. I'm multiplying it by x minus 3 over x minus 3. So I'm multiplying it by 1. Okay? So in this case, Marco, if x, let's say, was negative, it would be canceled out with this x. Do you get it? Yeah. Very good question, though. Okay, because he's identifying, oh, wait a minute, you are multiplying it by x. I'm not, actually. I'm multiplying by x over x. Okay? So even if it was negative, they would cancel out. Does that make sense?
So would it always be x over x?
No, it depends what you're trying to, what common denominator you're trying to create. Okay, in this case, we're trying to create x minus 3, x plus 1. So this numerator needs to be multiplied by the part of the denominator it doesn't have, right? You guys remember this, right? Yeah. This is from, elementary school, getting common denominators. Okay? So once we do that, then we can combine the numerator. So you expand, simplify. Your numerator ends up just being x minus 7. And finally, the last step is to find your boundaries.
Excuse me for the interruption, teachers and guests. If there's anybody who has a gray Ford Mustang parked in the east parking lot, I'm sorry, you are blocking somebody that needs to leave. If you could either let the office know and make them come down and move the car. Thank you.
Okay, here's where our boundaries come from. X plus 1, you're going to set it equal to 0. X cannot be negative 1 because that would give us 0 on the denominator. X cannot be 3. That's our other boundary. And finally, x minus 7 will be a 0 in the function, so we set x is equal to 7. There's our boundary. Put our factors on the left-hand side, the product of our factors on the bottom, figure out when they're negative and when they're positive, go back to the original question, which would be here, and find out that we want the positive values of this function. So it's not always negative. In this case, we're looking at these two values. So there's our ranges. Okay? And this number line also you should know, right? Very easy to create. Between negative 1 and 3, they're not equal to, so it's open circles. You draw a solid line between those two values. And then this is greater than 7. It should be an equal there too. So this equality, so this is a full circle, a solid circle, going greater than 7. Okay? Solution B, again, using graphing technology, they graph the two functions. They look for when this function is greater than this function. So they just look on it. They see these areas. It's tough to see, but you get the same ranges between negative 1 and 3. Negative 1 and 3, so here. And greater than 7 here. Can't really see them at all, actually, on that graph. Alright, summary. Solving an inequality means finding all the possible values of the variable that satisfy the inequality. To solve a rational inequality algebraically, this is the important one, right? Rearrange the inequality so that one side is 0, so moving everything to one side. Does it matter what side you pick? No, as long as you go back to the original equation and look at the side that you chose, and then you choose those ranges according to that side, because your answer will be opposite, right, if you switch sides. Okay? It doesn't matter as long as you go back to the original. Combine the expressions on the no zero side using a common denominator. So very important. This is what differentiates from the last section. Make a table to examine the sign of each factor and the sign of the entire expression on the intervals created by the zeros of the numerator and the denominator. So zeros of numerator and denominator. You have to check. Only when you are certain that each denominator is positive can you multiply both sides by the lowest common denominator to make the equality easier to solve. So for example, Nailed, when would we do this? What type of question?
For time?
When using or when dealing with time. Or what's another one that's always positive that we do a lot of work with? It was on your last test, the last question.
Size.
Actually, yeah, it was, yeah.
Dimensions?
Yeah, dimensions. Okay, dimensions, you can't have negative width, right? I would caution you guys with this though. Doesn't help to go the common denominator route, okay, if you just want to be safe. Takes a little longer, but I would caution you with kind of taking shortcuts there. You can always solve a rational inequality using graphing technology. Need to know when multiplying or dividing both sides of an inequality by a negative is necessary to reverse the inequality sign to maintain equivalence. Okay, this we learned I think in 5.1, something like that. You can solve an inequality using graphing technology by graphing the functions on each side and then identifying the intervals created by the vertical asymptote and points of intersection. For x values that satisfy this, identify the specific intervals where the graph of f of x is above the graph. Yeah, so that's obvious. You graph them both, and then depending on the inequality you're looking at, you look at the graph and see when they are higher or lower. You can also solve an inequality using graphing technology by creating an equivalent inequality with 0 on one side, and then identifying the intervals created by the zeros on the graph of the new function. So in other words, combining them and functioning them. Really, we're just focusing on the algebraic method. It's important to know these though, because if you get a multiple choice question on the test and it shows you a graph like this, you wanna understand it, right? You need to know, right? So if I say, you know, this is f at x in blue and this is g at x, and it's a multiple choice question and says when is f at x greater than g at x, you have to understand that you're looking for ranges where the blue is above the red on the y. Simple, right? But still, you know, don't skip it entirely. Don't not know what's going on. If you're given a graph, you need to understand how to read it and know when one function is greater than another, right? You just look at it, okay, blue's greater here, blue is also greater up to here, and then red is greater. Okay? Any questions on 5.5?